All right, we have a reservoir with particles, and we'll also be monitoring energy in it. So smaller reservoir, particles, and energy as well. Again, we'll have a total system, E total, and also have N total for particle number. ES and NS, and our reservoir ER, NR. Again, entropy is S equals KB log W. KB changes the units from heat to joule. The logarithmic comes from when we have two systems with various microstates, various W's, so W1 and W2, those would multiply together to get the total. But for entropy, they are additive. And so the logarithmic allows that property. Log of xy equals log of x plus log of y. So, and then that's entropy, and the W is the number of microstates. So we'll have E total is equal to ES plus ER, and N total is equal to NS plus NR. So now again we have the whole, and we'll have a fraction of pizza, or however you want to divide it to get the whole is your probability. How many, if you have 1/2, there's 2 parts to it, but the whole is still treated as one item, and those are parts. So we'll have 1 equals P, which is, there's a fly right here, proportional to omega R. Again, that will be plugged into there, the number of accessible microstates of the reservoir of X and Y, where X will be E and Y will be R. And we will rearrange those for NR and ER. So this is equal to omega R. You can do that right here, of ER, which is equal to E total minus ES, and NR is equal to N total minus NS. So now we'll plug this into this equation and rearrange for S. So SR AB that's right there, R. And we'll divide by KB and use E raised to vary the sides. Now we'll take f of x plus delta x, f of y plus delta y, and do a Taylor expansion, which the equation for f of x plus delta x f prime of x plus square root over 2 f double prime of x, and so on. And we'll also do that for y. Now the higher orders will cancel as you take the derivative, and that they become a constant. And so we'll just be left with these first two terms for those two. So we can write that out and just do this part of the equation first. F of x will be total delta x minus e to the s, f prime of x, partial s over partial e, plus n total f of y, f of, or delta y, f prime of x minus n to the s, partial s over partial n, and over kb, e raised to that is equal to omega r, and that's proportional to the probability. So now we can distribute this. I have E total plus E to the negative ES S partial E to the n total, direct over KB. Now, the totals will cancel. Again, they'll be constant. And when you normalize, they'll go away. So we just have these two left. So, omega R y is equal to ES partial S partial E over KB plus E negative NS partial S over partial N over KB. Alright, now the Maxwell relations or identities that we'll use. Entropy over energy at constant particle numbers is equal to 1 over your temperature, and entropy over particle number at constant energy is equal to your chemical potential over T. And so we'll plug those in respectively to those two. E negative ES 1 over T 1 over KB plus E to the negative NS mu over T 1 over KB. Combine those. Easiest way is use a beta 1 over TKB. And so that will plug into both those and you'll get E to the negative ES beta plus E to the negative NS mu beta. And that's your probability is proportional to that. And this is your grand canonical ensemble. Now, as opposed, two things, as opposed to the microcanonical ensemble, which you just had your box for your microcanonical of the total, and you have nothing from it because it's just one box, there's nothing exterior. Then we did a single deviation, and we showed that infinite regression is a problem there. It can't really exist because you continue to have to go. And so instead we did it with you modeling a single deviation, but saying it was a small reservoir in contact with some bath or some smaller system. And that gave us the other equation in the previous videos. Now, the other thing about this grand canonical ensemble is similar to the others as well. When you take the summation of all of the whole, you want to do the whole of it, take the summation of all the n values. So n starts at S and it goes to infinity. This is an n kind of starting to look like the mu. And you take the summation of all the possible energies. So E starting at S to however many there are, infinity. And then you write this equation, e to the negative ES beta, e to the negative NS mu beta. This equation has a name in statistical mechanics, and it's labeled as this. So when you see the horizontal I with that, this is the Greek letter G, and that's what it stands for. So this is your grand partition function, and that's where you'll see it, and important. But again, the single deviation is where we move from macro to this, and then to this one, which is there. And we're also doing particle number and energy. This is just energy or any flux, any single deviation. And then this is any of them.